Hi all. Today we see a very powerful numerical linear algebra algorithm called conjugate gradient method. It's a type of Krylov subspace method, and this conjugate gradient method is a very powerful algorithm to solve many uh, science and engineering applications problems, especially involving in diffusion equations. It's also used in training machine learning algorithms. So I hope to go through this to follow up this video. You have some basic understanding about numerical linear algebra, especially what does mean by n-dimensional space, uh, how those n-dimensional space are spanned by n linearly independent vectors, what does mean by orthogonality, and how does the orthogonality vectors or set of vectors span much better than arbitrary and linear independent vectors. Hope we start this algorithmic descriptions. So this conjugate gradient method was originally invented to solve this minimized quadratic functions fx equal to half x transpose ax minus bx, and we here the assumptions to apply conjugate gradient method is that matrix A is symmetric and positive definite matrix. So we all know that it's a quadratic problems that the solution is unique and that minimal solutions lies for solving gradient of that functions equal to 0. So this end up in linear equation called ax minus b. So ultimately, we conjugate gradient method is applied to find the solutions for this linear equations called ax minus b is equal to 0. It's an iterative algorithm where it iteratively tries to find the better solutions than the previous iterations. So we all know that there are some other iterative method like second order Newton method and first order steepen descent method. So second order descent method takes only few steps, but at every step we need to compute the Hessian matrix and we need to find inversion or some sort of inner linear solvers. And steeper descent method is a first order method, and it requires have a, not necessary to go for computation of the second order Hessian matrix, but it has a slow convergence for the reason that the steps are repeated in many iterations. So hence, to overcome these two difficulties, this conjugate gradient lies in between them. So the fundamental concept of conjugate gradient method is that an n-dimensional vector lies in an n-dimensional space, and that n-dimensional space is spanned can be spanned by n linearly independent orthogonal vectors. So those orthogonal vectors are not necessary to be computed at once. They can be computed at each iterative steps, and the solutions are updated. And the exact solutions with finite precision arithmetic can be computed after n steps, which is much better than going for a direct solvers taking n cube order of operations. This has a huge attractive to solve, especially for large and sparse problems, and they are also utilized for solving least square problems, minimization method, and other machine learning algorithms. The concept behind conjugate gradient method relies on the definition of what is meant by a conjugate. Two vectors defined to be a conjugate based on this property that if their inner product based on the matrix A equal to 0, and here we take some n linearly independent A conjugate vectors from d0 to dn minus 1, and A, as earlier based on this property, is a symmetric and positive definite matrix. So once we have this n linearly independent vectors, and the solutions which is also a n dimensional vector can be expanded in this n linear independent directions. And for the ith yeah, steps, we use only I number of uh, n linearly independent vectors, so which is subspace of the n dimensional space. And the error after this ith step would be x star, which is the true solutions, minus xi, which is expanded in this I dimensional subspace. So this once this vector computer vector and I step is substituted in the equations, there will be the b will not be exactly represented of this linear transformation. There will be a residual that is termed as an and gi, which is also an orthogonal to that subspace. And moreover, this e1 will also be assumed to be as an orthogonal to the previous search directions. So based on this property, we can make an iterative update of the solutions vector, like xi plus 1 is equal to xi plus alpha I di, because si is uses 1 0 to I minus 1 subspace, and then additional will be added on, and that will give you a better update than the xi. So based on the previous property that that the present error will be orthogonal to the previous search directions, and this once this error once xi minus been added on both sides and subtracted, this equations updated equations can be converted into an error equations, and that is being substituted in this equations, and we get the how to compute the alpha a, because this alpha a is being computed, then at each step this xi plus 1 can be computed iterative from steps I is equal to 0 to n minus 1. But however, this alpha I depends upon ei, which is an error vector. Um, so we know that if we would have known this ei, we would have computed the true solution at the ith step itself. But unfortunately, we don't know ei. So how does this can be overcome? By a small trick that uh, previously we told that we have an n-dimensional a conjugate direction that can be represented, that any vector like the solution vector in an n-dimensional space can be linearly represented in these expansions, and a is multiplied on both sides, and d transpose is multiplied on the both sides based on the certain properties, and we have ax star is equal to b, and alpha k can be computed without computing the error vectors. So these expressions can be substituted in the original expansion of the solutions vector, and we have this after n steps. We can compute the solutions vector and iterate in an iterative fashion. So it all depends upon this inner product, which is a conjugate with respect to other, except this I is equal to I, and all other terms will become cancelled out. So this again we this all the aforementioned things are crystal clearly explained again here. So we needed to have some iterative steps, like xk plus 1 is equal to 1, and this is a residual, and alpha is, can be computed based on this previously mentioned one. And this also says the similar thing, that expansion in a summation process can be done with this one, alpha 0 to alpha n minus. Here our in conjugate directions, our thing is to compute what is alpha 0 to alpha n minus 1. For that, we compute this alpha k equal to this term, and once that term is being substituted back, we get this kind of setup, and finally we get the same similar term, like it depends upon the search direction and the residual, and this alpha k can be iteratively substituted here to find out the find out the solutions in after n steps. So this is the foundation. So we have n linear independent a conjugate directions, and the expansion in the expansion scalar value is computed iteratively and updated to find out the true solutions in. But in some similar sense, we don't have a sophistication to have this n dimensional conjugate directions, and also it is very for a very large sparse matrices, n vector and going to the n step is also a very tedious process. So how to overcome these things are termed to be as a conjugate gradient method, and conjugate gradient method says that it's an iterative method, and not all conjugate directions are needed at a single moment, and they can be computed sequentially step by step at each step of the iterations. So this derivations this how that search directions are computed iteratively is what different from the conjugate directions method. So that iteratively updating the search directions is based on the residual of that solution at that particular steps. So here again we say that once we previous just try to recollect that algorithm one is similar to the conjugate directions. We have n linearly independent a conjugate vectors, and we compute the solutions of expansion can be at every steps can be computed based on the previous step itself. 0 to k minus 1 vectors are utilized to update k minus 1, and the present step we uses the dk conjugate directions with alpha k computed by here to update sk, and this is happen until n steps. But as mentioned earlier, that next the search directions can be updated sequentially using the current gradient and the previous search directions, and the current direction is nothing but the residual negative of the gradients. How do we utilize this one to update up to get the search direction is based on these equations, and these equations are put up into a loop similar to the previous one, and we not only computed alpha k, we also computed the search directions based on this equations, and this equation requires beta value. The beta values can be computed based on these equations, and once we get this beta value and the new search directions based on the previous search directions and also based on the previous gradient, we can update this vector, and alpha k is also depend upon the search directions that what we computed earlier, and also the previous residual. So here, what we bit tricky thing is it requires two matrix vector multiplications. One is ADK and ADK minus one. So the updated of the algorithm two will be algorithm three, where we overcome not necessary to have two matrix vector multiplication at every iterations. Rather than it would be necessarily go for only one matrix vector multiplication. That would be the trick what it is mentioned here. So similarly, that we are using the coefficient expansion, that residual term is nothing but gi. That gi can be updated based on that previous and the present search directions, and that tricky things can this part can be go to that alpha I. Then the alpha I can be very easily updated based on the only one matrix vector multiplications. This trick can be substituted in beta I update, where that matrix vector can be eliminated and put up only based on the inner product of the residuals. So this updated vector is algorithm three similar things, that we are iteratively updating the solutions vector using the conjugate direction vector. This conjugate direction vector is not computed at once from 0 to n minus 1. It is iteratively also updated through this uh, through these equations based on the residual and the previous search directions, and that coefficient of expansion for the previous search directions also computed based on the previous residuals, and the alpha coefficient of expansion is based only on one matrix vector by and the whole iterations is computational reduced compared to the algorithm 2 and algorithm 1. So this is a fundamental concept behind the conjugate gradient, which is a subpart of Krylov subspace method, where we linearly build Krylov subspace, and Krylov subspace are more efficient to solve certain problems like eigenvalue problems and linear equations that we will come across in maybe in the next video or after that. So this is a small scale example is given of a 2 cross 2 matrix, and initial vector is somewhat it is chosen somewhere here, and the updated solution the exact solutions can be computed from using a direct method. And that they're similar to the conjugate gradient method is first we need to find our initial residual. Based on the initial residual, we can update that initial residual itself will consider to be as a search directions, and based on that we can do compute the alpha 1. Then alpha 1 is computed, we can update that one. Then once that is been updated, we compute the next residual. The next residual is also the next beta value for computing the next search directions. The next direction is computed, the alpha 2 also computed. and that has been updated. So it is a 2 cross 2. It's at most 2 steps we could able to find out the solutions, which is somewhat very near to the solutions what we have computed here in 14 corporation arithmetics. So application I mentioned earlier, it's for science and engineering. It highly very much sophisticated algorithm to solve diffusions problem like heat diffusion equations or pressure equation in Navier-Stokes solvers. But also it can be applied in kind of engineering applications like image reconstructions, facial recognitions. Only the thing, how do we formulate a problem similar to like kind of a minimization problem or a linear solver. And also it can be used for in a deep learning algorithm. There are some variants of conjugate gradient algorithms that is suggested by different people like Fletcher Reeves, and which is not part of this video. Possibly we'll try to cover what are the other variants of conjugate gradient algorithm and what is biconjugate gradient algorithm to be applied for non-symmetric matrices, maybe in the next few videos. Oh, thank you for watching.